Hello, welcome to your second video on the binomial theorem. We are continuing where we left off in the first video. Please go back to that one if you haven't seen it yet. It's essential you watch that first. So, since the other one was fun, this one is part 2, more fun. Let's jump back to where we were. We were talking about this problem here. We were looking for the constant term of this expansion. If you were to expand this binomial, since it has a ninth power here, it would expand to have 10 terms. There's always going to be one extra term than what we see here because if you remember, the b component begins with an exponent 0 and the a component ends with an exponent 0, so there's always that extra term. So anyway, there will be 10 terms when this is expanded, but we are looking for what is called the constant term. What is that? Well, here's an example of a binomial expansion. So we have here x plus 2 to the fifth power. It has been expanded, and notice, like with this one, like what I just said, if we have a 5 here, there's going to be 6 terms. Let's check. 1, 2, 3, 4, 5, 6 terms. Again, that's because the a component, the first part here, will begin with the fifth power, then fourth, third, second, the first power, and then we can say there's x to the 0 power, which would be 1, and it's there. So again, there's one extra term because of that x to the 0. Let's look at the b component also. The b component would be first 2 to the 0 power, which we don't see anything here, then 2 to the first power, and it became part of the coefficient, and 2 to the second, third, fourth, and then 2 to the fifth. We don't see it there, but it is part of the coefficient. Okay, anyway, with all that, we can see this expansion has what is called a constant term. This is a constant term. It is a term in the expansion which is a constant value. There's no variable there, so that is like a fixed value, a constant. Okay, let's look at an example where there would not be a constant term. Okay, we have this binomial here, 2x plus y to the fourth power. When that expands, we get these 5 terms. Notice every term has a variable. And the reason for that is because the a component has a variable and the b component has a variable as well. So if they both have variables, when you expand it all, every term will end up with a variable. So that kind of expansion cannot have a constant term. So what that tells us about this one here is it must look like this one, and it does. We have a variable part and the other part is a non-variable, so there will be a constant term. And just like in this first example, the constant term will be the very last one because our first part of this expansion will be x to the fourth to the ninth power. And then it will be x to the fourth to the eighth power, and so on and so on. So the x's begin at a high power. So the constant's not going to be in the beginning, it's going to be at the end. Because at the end you're going to have x to the fourth to the 0 power, and that will be 1, and therefore all you will have is this part here. So it'll be just like this one. At the end there will be a constant. So this one has a final term that is a constant. So let's look at the final term. The constant term will have x to the 0, that's what we talked about. Hence, and it shows you basically the final term here. And how do we know that's the final term? Okay, so this thing again, there's a 9 here, so it will have 10 terms. And if it has 10 terms, the power on the b part in the last term there will be a 9. So in the 10th term, that power is 9. And we talked about that in the last lesson video, that the b exponent is always 1 less than the term number. So term number 10, this is 9. These two exponents always have to add up to what we see here, so this must be 0. And again, this is your a piece, this is your b piece, and then we have our coefficient in front, which is produced by this combination, and in this case we do 9 choose, and you always choose the exponent on the b value, so 9 choose 9. 9 choose 9 is 1. This becomes 1, so this is like 1 times 1, negative 3 to the 9th power. The negative then remains, because when we have an odd power, the negative remains. So it's like 3 to the 9th made negative, and that's what the answer is. Okay, that's a good one. It's important to know the constant term. Let's look at this last problem. It says the last term of this expansion. So it's kind of like the last one in terms of that we're looking for the last term, but this one will definitely, the last term will not be a constant term because we see a variable here and a variable here. So the last term of that, see if you can set that up. Well, the last term of that would be like this. Let's take a look. This thing again has a power of 7, therefore it will have 8 terms. So term number 8 is the last one. But when we're looking at the b component in term 8, it will have a power of 7. It always has a power 1 less, right? So that's 7. These two exponents have to add up to 7. So if this is the last term, this is 7, this is 0. And then we have the combination in front. And again, with the combination, we're doing this number, choose the power on the b component, which is 7. So 7 choose 7. So there's our full last term. If you do all the algebra there and exponents and all that, you will get to here. Why? Because 7 choose 7 is 1. This to 0 power again is 1. So it's 1 times this thing. So there's this thing. And then that's negative 3 to the 7th power. Again, it will remain negative because we have an odd power. And on the bottom, we have x to the 7th power. So there's our final answer. Okay, so hopefully the combination of the first video and this one has made these kinds of problems a little bit more accessible for you. And now let's finish with 2 challenge problems. And in our next lesson, we'll continue with more challenging problems, kind of like these two, but let's try 2 now. So here's your first challenge problem. The 5th term in an expansion, whoa, there shouldn't be a v there, in the expansion of this is this value here. So it tells you the 5th term looks like this. However, here you can see we have a and b. Those represent some values, some numbers, and here it says actually a and b are integers. So a and b are some unknown integers, but we can figure them out because we are told what the 5th term is. And that's our goal here, to find the values of a and b. What numbers can go there so that this is the 5th term produced by this expansion. So let's take the steps just like we would before. But first I'll give you a chance to try it out. See if you can set it up. Okay, let's begin. So let's begin like we did before. We have, we're setting this up. We have our A piece, which is AX. We have our B piece, which is BY. I didn't put the exponents yet. I didn't put the combination. So I'm suggesting you always begin like this. And then you jump to the B part, the second part, and you say, what is the exponent on that? Well, we're talking about the 5th term. So that means the exponent on here will be 4. Remember, the exponent on the b part, the second part, will always be 1 less than the term number. So that's a 4. Therefore, what's the exponent on this one? Well, we don't quite know because here is this binomial expansion is to the power n. We don't know what that is. But let's say that was a 10. If that was a 10, we would say this is 10 minus 4, or 6. You always do what that power is minus this one, and it gives you this one. So again, if that was 10, this would be 6. But we don't know what that is. It's n, so we're going to call it n minus 4. So n minus this number will give us what should be there. Okay, now what it goes on the combination. The combination is always this value, right? N. Choose the power on the b part, the second part. So n choose 4. Okay, so now we have this, but there's variables in there. There's the a and b variables, and there's also the n in there. So this is going to make it a little more complex. Let's take a look. So now we can go a step further, though. We know that this 5th term looks like this. And we can see that the power on the x one is 3, right? So this exponent here must produce x cubed. And the only way to produce x cubed from this is if there was actually a 3 here. So we are basically given that that must be a 3 by looking at it here. If this was something more complex, a 3 wouldn't work, but here it works. A 3 applied to there will give us that x cubed. So we know that's 3. So now we know this is 4, we know this is 3. So that tells us that the n value must be 7, because these always add up to what our power would be here. So there's 7, and now we have 7 choose 4, because it's always choose the b exponent. Okay, let's take it a step further. We know now this is the 5th term. And the 5th term, we are told, equals this. So we set that equal to what we have here. And 7 choose 4 is 35. This, when I put that exponent through there, a cubed, x cubed, and over here, b to the 4th, y to the 4th. So again, this equals this. Let's look at things we have in common here, because we can cancel them away. For example, let's go one step further. Yeah, that's what I did. So that y4 cancels with this y to the 4th. This x cubed cancels with that one because we can divide both sides by that. We can also divide both sides by 35. So the 35 cancels here, but when I divide 560 by 35, I get 16. So I've gotten rid of some common pieces. I've simplified this by dividing by 35. Now I have this. So 16 equals a cubed b to the 4th. This one now, at this point, you have to use some logic. What's the only way to produce 16? Can you cube some number to produce 16? I don't think so. If you had a 2 in here, 2 times 2 times 2 would be 8. 3 times 3 times 3 would be 27. So 16 cannot be produced by cubing some number. What about here? Well, if you put a 2 in here, 2 to the fourth, 2 times 2 times 2 times 2, that makes 16. So we just found out that there cannot be a number in here, but this to the fourth power 2 will work. So basically we've kind of deduced that b must be 2, since 2 to the fourth equals 16, and therefore a must be 1, because we want only 16 there, so this already produces 16, so that must be 1 to the third power. And that's how we get a and b values. One last challenge problem. Look at this one. This is a very common kind of problem you might encounter. Let's take a look. In this expansion, find the term in x cubed. So basically this will expand. Again, we see a 9 here, so that will expand to 10 terms, but only one of those terms will have an x cubed in it. All the other terms will have other powers of x, x to the fifth, x to the eighth, whatever. But one of those will have x cubed. And you're trying to find which term is it that has x to the cubed in it. The long way to do this would be to expand this fully and check. But there's a quicker way. So let's see if you can figure it out first. Okay, so I'm setting it up like this. We have, let's see, there's some unknown term where we're looking for x cubed. So right now we don't know what the power on this 1 over x is going to be. We don't know which term number we're talking about, so I can't put a number there yet. I can't put something there until I know the term number. So I'm going to call that r. And then that tells us that the power on the other part, the a part, must be 9 minus r, because we have 9 here, 9 minus r. For example, again, if this was a 3, then 9 minus 3 would be 6, and we would have 6 and 3, which makes 9 in total. So 9 minus r goes there. Okay, so what about the combination? Well, 9 choose the power on the b thing, so 9 choose r. So again, we have a combination and a whole term set up here actually through binomial theorem, but we need to figure out the r value now. So let's try. So what did I do? Oh, I ignored the combination. Why? Because all we're given here is that we need an x cubed to be produced, and the x cubed will be produced by these parts here, right? By this thing being to some power or this to some power. Those things combined, when they're multiplied, will have an x cubed. So I'm ignoring this because that's just going to be a number. That number is not important. We're just looking at the x part. So looking at this, we have that. This part is like this. And we know that when you multiply and combine and all that must be x cubed. So over here, 1 over x is like 1 over x to the r power, because we can put that r here and that r here, and 1 to the r, 1 to any power is just 1. So I leave that as a 1, and that r is now here. Now, when you have a fraction, you may remember by rules of exponents, if you want to bring that to the numerator, it becomes like this. You bring it up, and then the exponent becomes negative. So I did that so that I can now combine these. When I see multiplication of exponents with the same base, I can add the exponent values. So in this case, 9 minus r plus negative r is like saying 9 minus r minus r. So I'm combining those two, and that equals x cubed. Finally, that tells us that this exponent must be equal to this exponent. So 9 minus 2r, which is what this is, must equal 3, because we have x to that power and x to that power. The exponents must be equal. Here I can solve for r. Minus 3, move the 2r to the other side, and we can get r equals 3. So we have just found out that this value must be 3. And if the b portion has an exponent of 3, then that means we're talking about the fourth term, because remember the b power is always 1 less than the term number. So we've answered the question. This is term number 4. This is term number 4 contains the x cubed. And that's all we had to do here. Great job. Hope you did okay with these challenge ones. They're pretty tough. Maybe you weren't able to solve them, but I hope you were at least able to follow the explanations afterwards. Those are exactly the kind of problems we're going to look at in our next lesson together in class. They're going to be tough, but with this intro, you'll be ready for whatever I can throw at you. See you soon.